I built a Hilbert space model of reality, but not in the usual way. This isn't about wave functions or measurement problems directly. It's about structure, what is allowed to form, what can interact, and what actually persists once constraints are applied. The idea is simple to state, but it has consequences that aren't obvious at first glance. In this model, reality isn't just a state evolving over time, it's filtered. I define three operators: a formation operator, an interaction operator, and a persistence operator. Each one acts on a Hilbert space, but they don't commute, and that turns out to matter more than anything else. Because once operators don't commute, the order you apply them changes the result. If something forms before it interacts, you get a different outcome than if it interacts before it forms. And if persistence is applied last, it acts like a final constraint. What survives isn't everything that could exist. It's only what satisfies the full chain. So instead of thinking about reality as a smooth evolution, you can think of it as a cascade, a sequence of filters. Formation restricts what can appear. Interaction reshapes what's allowed. Persistence eliminates anything that doesn't satisfy the full constraint stack. What you observe is not the full space. It's what survives that ordering. To make this concrete, I built a small toy model using a finite-dimensional Hilbert space. In that system, you can explicitly compute the operators and their commutators, and when you do, you see something interesting. The non-commutativity isn't just mathematical. It creates measurable differences in what states remain accessible under different constraint orderings. That leads to a diagnostic. If you define a commutator between the forward operator chain and its reverse, you get a quantity that tells you how sensitive the system is to ordering. If that difference is zero, the system behaves as if the order doesn't matter. But if it's non-zero, then the structure you observe depends on the sequence of constraints applied. And that's the core question I'm exploring. Not whether reality is fundamentally quantum or classical, but whether what we observe is the result of an ordering problem. A constraint cascade where only certain structures are reachable, depending on how formation, interaction, and persistence combine. So here's where I want to stress test this. If this model breaks, it's going to break in the operators. Either the definitions aren't physically meaningful, or the non-commutativity doesn't correspond to anything observable. It could also fail if the toy model doesn't scale, if the behavior disappears in higher dimensional systems or continuous limits. Another possible failure point is interpretation. Am I just relabeling known structures in a different language, or does this actually produce new constraints, new diagnostics, or new predictions? So I want to ask you directly, if you had to break this model, where would you start? Would you attack the operator definitions, the commutator, or the idea that persistence can be treated as a final constraint in a Hilbert space framework? Because if this holds, even partially, it suggests something deeper, that what we call reality isn't just what exists. It's what survives the order of constraints applied to it. And that's a very different way to think about structure. If you've made it this far, then you already see what I'm trying to do here. This isn't about claiming the model is right. It's about seeing whether it holds up under pressure. Because if structure really comes from constraint ordering, then what we observe might not be everything that exists, just what survives the sequence. So if something feels off, if there's a place where this breaks, or if you see a better way to formalize it, I want to hear it. That's how this gets stronger, or how it gets replaced with something better. If you're new here, my name is Charles Carroll, and on this channel I explore how structure, information, and persistence shape the universe across physics, cosmology, and complex systems. And if you've been following along, then you already know. This is part of a much bigger framework we're building piece by piece. Thanks for sticking around. Join me next time. Who knows where the science might lead us?